Spawned from a 5-spacecraft mission called Themis, which was a magnetospheric mission looking at substorms in the Earth's magnetosphere. You can see here we have a wonderfully tortured acronym that our PI, Vasilis Angelopoulos, came up with. There's another one for Themis, which I'm not even going to try and replicate in real time here. This mission is basically Vasilis' brainchild. Unfortunately, he couldn't be here today. He sends his regrets, so you're going to have to take me, the deputy, instead. I can't talk quite as fast as Vasilis can, but I'm going to try and channel him and get through this as much as I can, and I'll try and remember to stand close to these microphones. So Artemis is 2 of the Themis spacecraft. We took them out to the moon. We've got a variety of different things that we want to study there, of the moon, on the moon, and from the moon. And here's just a sample of the orbits that we're in now. In a second, I'm going to show you a movie of how we got into these orbits. But we're in these very elliptical equatorial orbits. One of these guys is prograde and one is retrograde, so they precess at different rates, and you can see they sweep out different kinds of separations, and that's very important for many aspects of the science that we're doing. The periapsis is pretty unconstrained. It walks up and down. We get down to 10 kilometers sometimes. Sometimes we only get down to hundreds of kilometers, so we can do a variety of things in those different kinds of orbits. Let's see how this movie works. Go forward. I've lost control. I should be able to just push these forward arrows, right? Can I go back? I appear to be stuck, or else I'm pointing in the wrong direction. Here we go. All right. So here's the Themis mission. We're in these Earth-centered orbits. And you're looking at the 2 outermost Themis spacecraft in the red and the green there. You saw they just changed from Themis B and C to Artemis 1 and 2, purely a naming convention. And now we're starting our mission here. You can see that we're swerving out. We're getting farther and farther out in distance, and you're going to start seeing lunar flybys. We're going to dive by the moon, and we're going to get a little kick there, and we're going to dive way up out of the ecliptic into this big swooping orbit. In a little while, you'll see the other spacecraft do the same thing. Way, actually outside of lunar orbit we go, way up out of the ecliptic. All kinds of wild stuff before we actually get into lunar orbit. You'll see another lunar flyby here in just a second. And I'll show you some data from this one. And now one of them has captured, and the other one has 2, almost into lunar orbit. They're not actually in lunar orbit right now. They're orbiting the Lagrange points. One of them's at the near Lagrange point, and one is at the far. Soon, they'll both transition to one of those Lagrange points. And of course, the moon, in its orbit around the Earth, is going through the Earth's magnetosphere once a month. That's what's shown there. Now we're zooming in a little bit closer. You can see these guys just kind of wandering around the Lagrange points as we follow the moon in the moon frame. And soon you'll see them dive into orbit. So in a second, I'll show you the instrumentation on this mission. It's very complete plasma instrumentation. We have a full suite of fields and particles instruments, and all of those are very healthy currently. The only issue we've had is that we lost one probe from one of the electric field booms to what we think was a dust impact. Luckily, we have 4 of those probes on each spacecraft, so we have a lot of redundancy there, and we have not lost any science. So here we've landed in our final lunar orbits, these nice elliptical guys. We won't watch these long enough to see them precess very far, but I showed you the snapshot before, how they precess around. We get passages through the wake. We get periapsis passes at various solar zenith angles. We get all kinds of interesting conjunction cases, and we get cases where they're very far separated, where one's an upstream monitor and one is downstream. So it allows us to do a really good job of separating stuff that's lunar from stuff that's not lunar. And here we are drifting serenely around the moon. Okay, now let's see if I've got control back. Or maybe someone could just advance the slides for me, since I can't seem to do it with this. So here's the instrumentation. 5 instrument packages measuring the full range of plasma and fields and energetic particles. The spacecraft spins around. These are the fields of view of the particle instruments, so we get a full distribution of the plasma every 3 seconds as the spacecraft spins. And I still can't advance. Next slide, please. So here's the system that we're studying. This is the moon as seen by a plasma physicist. There's all kinds of stuff happening around there. It's actually not all that serene at all. The takeaway from this graphic is that the moon is just being bombarded by a hailstone of stuff out there. It's getting hit by plasma and energetic particles from the sun. It's being hit by UV from the sun. It's also being hit by micrometeorites. And all this stuff is just sputtering all kinds of nonsense off of the moon. We're getting photoelectrons coming off the moon. We're getting ions from the exosphere and the surface. We're getting solar wind plasma interacting with crustal fields. We're getting a wake forming downstream. And Artemis flies through all of this, and it sees all this stuff at various distances from the moon. But what I'm going to show you is that we can trace a lot of this stuff right back to the surface. So we can see, pickup ions way out here, and we can trace them back near the surface where they came. And that's kind of a theme for the Artemis mission. Next slide, please. By the way, we do some non-lunar physics. I won't talk about this slide. Next one, please. Here's the first orbit of Artemis. Actually, this is the first passage by the moon by Artemis. We actually weren't in orbit yet. This is in one of those very early swing-by orbits. So this shows kind of a sample of our data, plasma data. Here's the wake region here. You see the ion flux drops out, the electron flux drops out. Here's this nice profile of the ion density. This matches basic plasma theory perfectly. But there's a lot of interesting stuff here on the kinetic level that does not, that's very interesting. We've published about 3 papers already on this wake crossing, so if we do that on every orbit of Artemis, we'll have about 10,000 papers. I don't know if we'll be quite that productive on everything. I just wanted to point to this simulation. I think it's the first time that anyone has ever looked at the dynamic wake as the solar wind conditions that are driving it change. So that shows the excellent agreement between the simulation and the measurements as this wake is flapping around and twisting as the solar wind conditions pass it. So this is all very plasma physics-y. Let me start to get more planetary. Next slide. So let's talk about reflected protons. One of the first things that we saw with the Artemis mission as we're flying around the moon, here's the solar wind coming in. It's a narrow beam in energy and angle. But here's all this other stuff when you're flying by the moon. What is this? Well, with Artemis, since we have all the fields, we can trace these guys back to where they came from. And lo and behold, they all come from the day side, kind of in the southern hemisphere. And if you look at a crustal magnetic field map, they're all coming from right around here, right where all these strong fields are. So this is actually solar wind protons that are being reflected from strong regions of crustal magnetic fields. And what's more, they're being reflected more efficiently than we think they should be. So it's pointing to an efficient reflection process. We think it is to do with an electron-ion coupling process and electric fields that develop in these things. But whatever the reason for this efficient reflection, the protons are reflecting extremely efficiently from these strong crustal magnetic field regions. And we think it may be pointing to support of a solar wind shielding mechanism for these swirl formations. So we can actually even talk a little bit about geology on this mission. I think Lon Hood figured this out about 40 years ago, but we're really, I think, finding support of his theory yet again. Next slide, please. Talk about lunar surface charging a little bit. The moon is a big piece of insulator sitting in a plasma, so it charges up because it's being bombarded by electrons and protons, and it's being bombarded by UV photons and photoemitting. The basic expectations are that in the night side, where there's no photoemission, you should charge up negative. That seems to be borne out. On the day side, you should charge up positive because you're a photoemitting surface and you're boiling off all these electrons and leaving a positively charged surface behind. That is not what we're finding. We're finding that the day side very often charges up negative. It's completely non-intuitive, and it goes against what we really thought before coming here, although if you dig into the literature, there's some suggestions that this should be the case. Next slide, please. So how do we find this out? Well, we find this out by using the electrons as remote tracers. Half of the electron distribution goes down to the surface and comes back, and it tells you what it did there. So if you look at the velocity space distribution of these electrons, everything in this little wedge has gone down very near the surface and been magnetically reflected. And if you look at the boundary of this cutout here, it tells you what the electric and the magnetic fields are below you. At the same time, there's this bright beam of electrons coming up from the surface. That's stuff that's actually being emitted from the surface, either from secondary emission or photoemission, and it's getting accelerated up to you. The moon is basically forming a big electron gun here. So we can see the top end of this electron gun, and we can trace it back, and we can find out what's happening right near the surface here electrostatically. We're talking within meters of the surface. Next slide, please. I don't know why I keep trying to click. I'll just ask. So Andrew Poppy, who's responsible for about 25% of the scientific output of the Artemis mission so far, has modeled this process. And these are the kind of potentials that he can find. And you can see it's not a typical sheath. There's a little photoelectron sheath here like you expect, but then there's this big structure on top of it, and the whole surface is floating down negative. Again, we're using these electron beams as a tracer of that. Here's the electron beam. This is the flux ratio between down and up, so it's showing this very bright beam coming up. And here's Andrew's model, and it's fitting it very, very nicely. And he's actually taking into account the electron and the ion currents here, and the photo emission, and he's getting all this to come out right. So this is really interesting stuff because this has absolutely fundamental implications for what's happening right near the surface. Any ions that are created near the surface are going to feel these fields. If there's dust floating around near the surface, as there are suggestions, it's all going to feel these fields. So this is really interesting stuff. Next slide, please. And we can see all this with Artemis because on a magnetic field line that's connected to one of these regions where there's this interesting potential distribution, or a field line that's connected to somewhere where these protons are being reflected, it perturbs the plasma all the way upstream along these field lines. And you get all kinds of waves. You get all kinds of processes happening upstream. If I could get the next slide, I'm going to show my one horrible plasma physicist plot of many, many panels. Sorry about that. We can't resist from time to time. But I want you to focus particularly on one panel, which is the smallest one here. It's this little bar. And when this goes from blue to green, that tells you that the magnetic field, which is wandering around, flapping back and forth, that tells you the magnetic field from the spacecraft is pointing at the surface. So you're connected to the surface. And now look what happens in every one of these panels when that happens. The plasma goes nuts. The ions get disturbed. The electrons get disturbed. Actually, both ingoing and outgoing electrons are getting disturbed. So this is disturbing plasma that's actually coming towards the moon as well as going away. The waves absolutely light up. These are electrostatic field waves. These are magnetic waves below the cyclotron frequency, just lighting up. The whole plasma is going nuts. It's ringing when you're connected to the surface. And it's because of this stuff happening at the surface, propagating out to you. So now with Artemis, we can look at this stuff and we can sort of trace it back to the surface and try and learn about what's going on right at the surface. Next, please. The last major topic I want to talk about is pickup ions. So this is the cartoon. You can tell it's a cartoon because these orbits aren't the right shape, but there were only so many pictures of fountains that I could find online and saturate to make a pretty graphic. So, but this is the basic idea. Here's your Artemis probes flying out here. These ions are getting picked up, accelerated from near the surface, and they follow trajectories which are mass dependent. And with Artemis, we can cut through those, we can measure them, and we can try and understand what they're telling us about the near-surface exosphere and the actual surface from sputtering. Next, please. Of course, all these things are coming from the lunar exosphere. I stole this beautiful graphic from Dana Hurley, which shows all the things that are going on in the exosphere. I'm not going to try and talk you through every single one of these things, but it's a very complicated coupled system. It's being driven by all the inputs I was talking about: photon flux, plasma flux, micrometeorites. There's recycling to the surface, there's migration of species, but ultimately, most of these neutrals' ultimate fate is to be ionized and picked up and carried away in the solar wind, and that's where we see them with Artemis. Next slide, please. So this is their actual trajectories that they follow, not the cartoon anymore. This is the simulation. You can see they feel the effect of the solar wind electric and magnetic field. They follow these big swooping cycloidal trajectories. We fly through them, you know, cutting across this kind of part of the cycloid with Artemis, which I'll show you in the next slide. So here's a sample of Artemis data. Again, the big red stripe down here is the solar wind, and here's these faint traces of pickup ions up here. This is the prediction of the energy you should get for an ion coming from the surface, this black dashed line. So you can see it's matching up very well with where we think pickup ions should be in energy. In angle, they're very narrow as well. This is a very field aligned, it's not field aligned, it's a very narrow, perpendicular to the field, actually, plume of ions coming out at you. And Artemis is seeing them way out to the side of the moon. They're being accelerated right along this electric field and starting to bend back around the magnetic field. And we're seeing them here. And actually, in this case, we saw them with both probes. Next plot, we've done some statistics on this. And did I get the thank you. We don't have a mass spectrometer on Artemis. Boy, I wish we did. But we have a poor man's mass spectrometer because we fly through these trajectories and we can see what direction they're going, we can see where they are in physical space, and we can start to at least place constraints on what the species are. So this is what they're allowed to be. You can see most of them point towards something in the mass 20 to 40 range. If you go further than this and you make an educated guess that they are most likely to come from near the surface, you can start to try and build up a mass histogram. We're still trying to understand the details of this, but it has some very intriguing peaks around mass 20 to 24 and around mass 40 there, which might make you think about alkalis. Thank you. If we can just click forward like 3 or 4 times, there's some labels of, oop, that's interesting. This is fine, stay here. There were a bunch of little labels that were going to pop up there, but you guys know where those masses are. So this is just to show you that we see more than one species. Again, we're looking at ions in velocity space now, and you can see these multiple populations of ions. This is the solar wind right here, and then there's at least 3 groups of ions here with different energies and aligned with different rings. These rings are where you expect different mass pickup ions to fall in velocity space. So we're seeing multiple species, and we think multiple origins. You can see these guys have different energies, so they've got to come from different points on the moon. And you can see that also in the energy spectrogram. Instead of the narrow feature we saw before, this is broad, and there's a couple of stripes to it. These red and black stripes are corresponding to ions that come from right below you at the surface or right from the subsolar points. They're kind of in that whole range there. And we're just getting started on unfolding these and trying to fit these to models of what kind of exospheric distribution could give you this, but it's going to be really exciting. Next slide, which I think is my last, I hope. Oh, we also see pickup ions in the magnetotail. This is really interesting because you're turning off about half of the things that produce exospheric species because you're turning off solar wind sputtering. So this could potentially be a whole different group of pickup ions, and of course, the fields that they experience in the magnetotail are very different. So this is it gives us an extra handle maybe on what's coming from the moon. Finally, my last slide now, I think. I just want to kind of make a pitch for Artemis-LADEE collaboration. Artemis and LADEE are going to be great. LADEE is measuring the neutrals, the dust. It's measuring this really interesting coupled surface exospheric system. Artemis is measuring a large proportion of the things that drive this system. So having the 2 of them there together would be really amazing. And furthermore, as you've seen, Artemis is measuring some of the outputs of this system. It's measuring the portion of this exospheric population that gets ionized. So you've got Artemis with the drivers, LADEE with the dust and the exosphere, and Artemis again with some of the products of this system. So I really, really, really hope we can get both of these missions there together, and I think it's going to be great. Thanks.
Okay, we're going to take 2 questions. And there's the microphone.
I think that Bob Grimm was going to do some EM sounding using Artemis data, as I recall.
Yeah, so Bob Grimm and Greg Delory have both been working very hard on that. It's a tricky problem, but they're making progress. I wasn't proactive enough to get in touch with those guys and get some slides of their progress, but they're definitely working hard on that and making progress.
We're working real hard on it.
There's Greg. Buttonhole him in the hallway and he can tell you about the details.
Okay, and if the question is too faint to hear, could you please repeat it?
Okay, thanks.
Okay, another question, one more? Here, you go, Rich.
What produces the negative day-side potentials that you think you see?
So what seems to be happening there is that it's actually a distribution of space charge that's being built up. Basically, the current of the photoelectrons is so big that it's actually producing this space charge distribution there, and that acts to build up this kind of hump in the potential that reflects most of the solar wind electrons on one side, reflects most of the photoelectrons on the other side, and kind of squeezes them apart. So that's the best that I can explain it to you in 1 or 2 minutes. Andrew Poppy could give you a much better explanation of that, and he's here.
Great. Let's thank Jasper again.